welcome back. This is the homework number 6 review video. This homework had 4 problems, and getting started, the first problem, we were given a description of the zeros and poles, and for the first part, for part A at least, we just needed to write out what the expression for the transfer function for the plant was. So that's what GP was. Okay. So getting started, we wanted to figure out what the expression was. We have a polynomial in the numerator and a polynomial in the denominator, and that's what we're looking for. So we know what the roots are to each of those polynomials, so we're kind of working backward and forming the equation itself. So we can go element by element for these solutions. This is the numerator, so this will be the zeros. We have a -1 solution, so that should correspond to a piece of the polynomial with s plus 1. Similarly, we have an s minus 2, which should correspond to a solution at plus 2. And then also similarly, we have an s minus 3, which should correspond to a plus 3 solution. Okay, we do the exact same thing for the denominator. Now we have 2 zeros, that'll correspond to 2 free s's. So that you could just plug in similarly to these other parts, but it would just amount to a single s by itself. And since we have 2 of those solutions, we'll have an s squared. Then we have an s minus 5, that should correspond to a plus 5 solution. Then we have an s plus 2, that should correspond to a -2 solution. So if you want to check your work, you would just go back and solve each piece of these by setting them equal to 0, and the solution should be your poles for the denominator, should be your zeros for the numerator. Okay, and that completed part A. So this was our expression for GP that we ended up with. For part B, we need to express this in a time domain type of solution. So this is similar to some of the earlier examples that we had done in previous lectures, where we have a transfer function and we just want to go back to the time domain. Okay. All right, so you will form an output over input ratio, and you just want to cross multiply this through. Okay, and once you get that done, you will take the inverse Laplace transform. So that's all we've done right here. I elected to use y of s over r of s here. You could use u of s. Either variable is fine for the denominator. And actually, I did end up changing to u here, so I expressed it both ways here in this bottom equation. So all we did was take the GP from part A, cross multiply. We end up with this equation, expanding it and simplifying it, and then also expanding out all of the s terms, and then taking the inverse Laplace transform here, we now have an expression that is in the time domain. Okay, so every time we have an s, we would have a derivative that corresponds to it. So the s's essentially become dots in our lower equation. Okay. So here I've expressed it with r as the input variable, and then here I've expressed it with u as the input variable. Now, I felt like it was better to use the u for the next part. So, or actually part D rather is what I'm talking about, but let's look at part C. So in this problem, we had a situation where we wanted to track a command signal, and in order to do that, we wanted to write out the first 3 of the GC to trial designs. So to do that, we needed to first determine how many free s's we needed. In this case, we need 2 free s's to track the command signal. We have no disturbance, so that's not a factor. 2 free s's, but if we examine GP, we actually have 2 free s's in our expression for GP. So there are 2 free s's right here. So actually our GC design did not need to have any in it because we already have them in GP. Okay, so that made our GC design very simple. We have KC over 1 for the first trial design, KC over S plus A for the second one, and then KC times S plus B over S plus A for the third one. Remember, when you're making these trial designs, you always want to see the previous design within your design. So for this middle design, say we have KC over S plus A, we should be able to see KC over 1 somewhere in here, and indeed we do. We have KC, and then we have this 1 that's not written out, okay? So each one should be like that. They have a multiplication occurring, but the original design is somewhere in there. Okay, part D. So we just use this time domain expression, and what we want to do is draw the math flow diagram using the Vannevar-Bush nested integration technique. So we just preserve our expression from the end of part B, and we move all the derivatives to the left-hand side, all the non-derivatives to the right-hand side. Once we have that, we will integrate, so that's the step right here. We integrate each part of the left-hand side individually, and each part of the right-hand side as a group. So here we only have 1 term, but it would be, if we had multiple terms, they would be integrated as a group. Okay, once we complete that step, we will have at least 1 term. So here it's just a negative u right here, that we will move over to the right-hand side. So we can't have any non-derivative terms on the left-hand side in order to keep going. So we move that term over here. It's best to move it in front of the integral. That way you don't get confused with what actually gets integrated or not. And then we will go ahead and repeat that integration step and continually refactoring. Now we're left with 2 terms that need to be moved. So in doing that, we are left with this equation right here. Again, we refactor. We have another 2 terms to move over. We move them in front of the integral here. And then we integrate our last time. And we're left with a y of t expression. We should expect to get an output signal equal to something, some expression here. Okay, so we work this way in the equation, and we work this way in drawing the diagram. So we start with our y of t, we draw that. The first thing we encounter is an integrator, so we draw that integrator in. Going into the integrator, we have 3 elements, this integral of stuff, a u, and a y. So we have a summation with our u, our y, and our integration of whatever goes into it. We don't worry about that until we write our integrator. Okay, so we're at this stage right here and at this stage right here in the equation. Now, within the integrator, what goes into it, we have 3 elements here. So a 10y, a negative 4u, and an integral of more stuff. Okay, so the 10y, we just loop that around and connect it and have a gain block that's added in. We have a negative 4u, so I opted to put the negative sign on the summation junction here. You could have put it in the gain, and that would have been fine. Either way works. And connect that in. And then we have this integrator. So we have that here, and that's added in. Okay. Now we're able to peel away the integral and see what's inside. Okay, so we now have 2 elements that we need to go into this integrator. We have the u, which I put at the very top of this diagram, so I just pulled it down here with this common line and added it into summation block. And then we have the integral of the 6u. So actually we have a u here, and we have an integral of some gain times u. So our gain happens here, and then I opted to put the integrator right here and add it into the summation right there. I thought that kind of gave it a clean look. So sometimes that happens, sometimes it works out very neatly like that. And so that's our completed math flow diagram. Okay. For problem number 2, this was a lot of GC design, and actually problem number 3 as well. So we had 2 different circumstances. For problem number 2, we did not have a disturbance, and for problem number 3, we did have a disturbance. So for problem number 2, our problem was to track a set point. So this was a set point regulation problem. We had a GP given here with s plus 3 over s minus 15. There was no free s here, note, but we do need one in this problem. Okay, so in that case, we need to design one free s within our GC trial designs. Okay, since it was told that you were using the standard system block configuration, which is drawn right here. This is a little representation of it, that meant that your QCL equation, which we derived a few lectures ago, is actually this one right here. So this one's pretty easy to use. We just plug in the different elements. Okay, so the first three trial designs you would have come up with that incorporate the free S are GC over S. Then if that didn't work, I'm sorry, I said GC over S, I mean KC over S. The next trial design would have been KC times S plus A over S. And then the third one would have been KC times S plus A over S times S plus B. Okay, so we try GC number 1. So we plug in the P sub P, the Q sub P, the Q sub C, and the P sub C. So these are the numerator and denominator polynomials of both our GP and our GC for our first trial design. Okay, so and that plugs right into the QCL equation. Okay, so I've just written that right out here. All the which element is equal to what. In general, just the P is the numerator. So we have a PC is KC. P sub P is S plus 3. And the Q is the denominator. So Q sub P is S minus 15. And Q sub C is just S. So we plug that into our equation right up here. And I've written that out right here. So all we did is simplify it. And then we want to look at our necessary and sufficient conditions. Okay, so I called this equation star. So we always try to get to that equation star. And this is the thing that we would compare against, our model equation. Now in this problem, you're asked to place all closed loop roots, all poles that is, at -3. Okay, so we look first at the necessary and sufficient conditions, and we see that we can satisfy those with a selected K sub C. Okay, so this would work, except when we go and form our model equation for the closed loop poles all placed at -3, so that's a second order equation. Once we expand it out, we get that what I call equation pointy star right there, the bolded one. When we compare these and form our equations for our control gains, we find that we actually can't solve for that. They have no solution. So when we compare the asterisk type star and the bolded pointy star together, we get these equations here, and we can't solve for these. So trial design number 1 did not work for where we want to place our roots. So we're going to have to advance to trial design number 2 in this case. Okay. For trial design number 2, we just advance to the number 2 trial design right here for GC. We plug that again into the same QCL formula, and we try to solve it. To make this monic, the step you'll do is divide KC plus 1 for all of these coefficients. Compare again to that bolded star equation, that's our model equation, to place all the closed loop roots at -3, and then you'll find that there is no solution for this as well. So trial design number 2 didn't work, but don't worry, trial design number 3 did work. So once you use trial design number 3, which we have right here, KC S plus A over S plus times S plus B. So we wrote that out, plugged it into QCL, compared with our now model equation that is a third order. We do have to rework this, and we should have 4 terms in it. We compare this equation of the QCL to the new bolded star. So we call that new asterisk, new equation star, and new bolded star equation. These two get compared. Form these 3 equations, and then you can solve for KC, A, and B. Okay, you should come out with A equals 3 over 7, B equals 3, and KC equals 21. And those should be the values you found. And once you plug those into GC, you should find that you have 21 is our value of K, times S plus 3/7 over S plus 3, okay? So that one works. We actually can plug that back into QCL and just check. If we plug it back in, then we should expect to get this equation bolded star out. It should look exactly like the ideal roots. So we've done that here, actually right here, and we find that we do end up with that equation. So yes, trial design number 3 for problem number 2 did work. Okay, problem number 3 now. We want to track a command signal, and we also have a disturbance present. Okay, so the disturbance is a stepwise constant, so that implies 1 free S being needed. However, for a command signal to be tracked, you need 2 free S. So the total needed is actually 2 because you choose the bigger value between these. You don't add them. We don't need 3 free S. We need 2 free S because that is the bigger need. Okay. You can also compensate for the disturbance by tracking this command signal. Okay, so these are not additive. You just choose the bigger one. Okay, so 2 free S needed. However, when we look at our G sub P, we see that we actually have 1 free S supplied. So in that case, we only need to design our GC with 1 free S. Okay, so 1 plus 1 equals 2, so we need to add our 1 for GC. Okay, so that makes our trial designs for GC KC over S, KC times S plus A over S, and KC times S plus A over S times S plus B. Okay, you were asked to supply 3 trial designs. It may have been beneficial to write out the 4th one. We'll get to that in a moment. We were also asked to place all closed loop poles at the ITAE optimal locations. For this problem, there was not a omega sub n given to you. You could have left it symbolic, or you could have chosen one. Either would be okay. So here we go ahead and try GC trial design number 1. Once we plug this into our QCL, now I didn't specify if you were using the standard block diagram, but if it's not given to you, that's what you assume. So QCL equation, just the same as problem number 2. Okay, we plug in the P polynomials and the Q polynomials, and then we find that we cannot satisfy the necessary sufficient conditions. Trying trial number 2, we find a very similar kind of status here. We again have this negative sign here, so we cannot make this term positive at all. We have no control over that term. So we can't satisfy the necessary and sufficient criterion for stability here either. So we try number 3. We plug that in. This is, we're calling equation star. And now for the ITAE, you would use row number 4 here. So instead, since it was a very large equation, 4th order equation, I went ahead and compared to the ITAE table. I used the ramp input table, but since it wasn't specified that, if you use step or ramp input, either one was acceptable in this case. Okay, I used ramp because we're trying to track a command signal, and that makes a little more sense than the step input table. Okay, so we write out our equations and we get these equations here. However, if you try to solve these, no matter what your omega sub n is, you won't find any solutions. We really can't solve these. Okay, so let's advance one more GC trial design. Okay, so trial number 4 would have been the KC times S plus A times S plus C over S times S plus B, which you will see appear again later in sim number 3. So we plug this into QCL, we try and solve it, and we compare to our equation star, which is exactly the same ITA row as we were just trying with trial number 3, so just this row right here, and we should end up with these 4 equations. Now, if you chose a value for omega sub n, you were able to go ahead and solve for values. Having an omega sub n equal to 2 would have resulted in real values, so I just wrote out example values here for that particular omega sub n in this solution. Okay, So that one did work. All right, last problem in this homework set. Problem number 4. This was root locus sketching. So you were given 3 relatively simple root locus sketches to, or asked for root locus sketches. So 3 open loop transfer functions were given. For part A, we have a k times s over s minus 10. The first step is, of course, to write out n, m, and q, and then find the values of the zeros and the values of the poles. So for this problem, we have 1 0 because the polynomial on the numerator is of order 1. We have 1 pole because we also have a polynomial of order 1 on the denominator. And so n and m are both 1. So poles, zeros. These are the numbers of poles and the number of zeros. We calculate q by subtracting n minus m, and we have 0 virtual zeros. That's what it tells us. Q is the number of virtual zeros. Okay, so then we solve for what is the zero at, or what is the zero value. So we take the numerator and just set it equal to 0, and that means that it is actually 0. That's the only value that solves it. Do the same for the pole, and we end up with the value positive 10. So if we set s minus 10 to 0, we should find the solution of positive 10. Okay, so the first step is then to place your points on the graph. We use x's for poles, circles for zeros. So I've marked both of those here. We then have, notice that you have 2 elements on the real axis. So anytime you have anything on the real axis, you want to apply the real axis rule. So we do that. We move our pen across here and we look rightward, move leftward. And so we count the number of odd elements, or rather we count the number of elements and look for the odd number. Anytime it's odd, we fill in the branch. So we have 0, 0. Once we move past the 10, we have 1. That's odd, so we can fill in the branch. So this becomes bolded until we pass the 0, and then it's even, because we're looking rightward, we have 2 elements, the 0 and the pole, so 2. And so nothing gets filled in past that point. Okay. Now we know in general the migration paths are the poles move to the zeros. So that sets our arrow right here. So the pole is moving to the 0. We have no virtual zeros, and really there's nothing else to fill in here. So this is our completed locus for part A. And if we were asked to supply, in this problem you were asked to supply, is there a value of k for which this is unstable? And the answer is yes, it is actually unstable for all k. So anytime the branch is in the right-hand plane here, we have an unstable situation. It's actually unstable for all values of k. It starts at k equals 0. That's where our points are actually just marked. And then any movement is a growing value of k. Okay. So problem number B, or problem letter B out of number 4, we have GOL equals k times s minus 3 on the numerator and s times s plus 10 in the denominator. So if we look for our value of n and m, first looking at the numerator, we have an order 1 of s. So m is 1. There is one solution to this if we set it equal to 0. Okay, that solution happens to be positive 3, so that is the value of our 0, but our value of m is 1. Okay, do the same thing for the denominator. How many solutions are there if we set this equal to 0? And that is our value of n. N is 2 here because we have an s and an s plus 10. Okay, now if we do set this equal to 0, we solve for our poles. We have 1 at 0 and 1 at negative 10. Okay, those are our 2 solutions, so those are our values of our poles, but n is 2. Okay, let's calculate q. Q should be n minus m. That's 2 minus 1, so we have 1 virtual 0, and that's what q is, 1 virtual 0. All right, so the order of what you should do in this problem to complete the sketch: first, mark the points. That is the positive 3, the 0, and the negative 10. And then we'll apply the real axis rule and indicate the directions. So looking here, we've drawn our sketch in, and we have our 0 here at positive 3, we have our pole at 0, and we have our pole at negative 10. Okay, since we have elements that are poles or zeros, or both, on the real axis, we apply the real axis rule. So we move our pen across here and look rightward. So we're here how many things we've passed, how many things our pen has passed. If that is an odd number, we fill in the branch, so just like normal. So moving this across here, 0, and then we pass 1, so it's odd, and we fill in the branch. We fill in the branch until it becomes even, which it does once we pass the pole at 0, okay? So nothing is filled in past this point until we pass this second pole at negative 10. It's now odd because there are 1, 2, 3 past our pin, and so we fill in that branch. It actually never becomes even again, so we fill it in to negative infinity. It just keeps going. Okay, again, we know in general the migration paths happen from a pole to a 0. Poles go towards the zeros, so we can fill in our direction arrows here. So this pole goes to the virtual 0, whereas this pole goes to the actual 0. Okay, and that is your completed locus. Now, to answer the question, are there unstable values, or are there values of k for which the system, this closed loop system, is unstable? And the answer is yes. It's actually any k because we count the endpoint of 0. So anytime there are roots at 0 or in the right-hand plane over here, we're going to have an unstable situation. Okay. All right, for part C, this was the last problem, the last sketch. We had a GOL, and we should have had a K here, but it looks like on the assignment sheet that I had forgotten to write the K. The rest is here, but the K should have been here as well. Otherwise, it really kind of doesn't make sense. So I do apologize for that, and I hope that didn't confuse you when you're working this. It wasn't intentional to leave that out. But if you're evaluating the transfer function portion of this, you will look for the number again, N, M, and Q, and then find what the poles are. Or if we had zeros, we would find out what those zeros were as well. So here, looking at the numerator, we actually have no zeros, and so M is equal to 0. So we have no S's up here, okay? N is the number, the order actually, the number of solutions we have in our denominator, the number of poles we have. So we actually have 3 because we have a third order polynomial down here. Okay, so N is 3. We can then calculate Q. Q is N minus M, and we have 3 virtual zeros. Okay, we can solve the polynomial. Our solutions would come out to be 0, -3, and -3. So those are the values of our poles. Okay, so what we want to do here, just kind of the order of things you do, plot your points, place them on your plot, apply the real axis rule. Here we're going to apply the collision rule right afterwards, and we'll get into why, and then solve for the breakout points. And here we actually have just one breakout point, but let's go ahead and plot the points first. So we know that our poles are at 0, -3, and -3, so we have an x at 0. We then have a double x, or a crosshatch, at -3, so we want to show that very clearly that we have 2 poles at -3. And then since we have things happening on the real axis, poles or zeros or a combination of the both, we would apply the real axis rule. So once again, we move our pen across here, look rightward, and count the number of elements that we cross. So here we cross 1, so it is odd. Fill in that branch. We cross 2 more, so that total is 3. It's still odd, so we continue filling in, and actually there's nothing else to cross. So it's going to remain odd all to -infinity. So we actually would just fill in that branch all the way to -infinity, okay? Now I can see at this point we don't have yet the breakout filled in. We can see that we fit the criteria for the collision rule. One of these poles and this pole move towards each other. If they move towards each other on the real axis, they will collide and deflect off at ±90-degree angles to the real axis. So that should happen. They move towards each other, and then they collide and deflect off. Okay, there is not a zero between them, which would negate applying this rule. So we know that this happens. Okay, so in order for them to move, we know this one of these poles is leaving the -3 point. It's moving in this direction, and this pole is moving in this direction. So this collision should happen somewhere around the -1, -2 kind of point. We can solve for what that is by applying the breakout formula. Okay, as for the other pole at -3, it's going to move towards the virtual zero, so it keeps going out here. We do have 3 virtual zeros, keep in mind. One of them is going to be over here, and then the other 2 will be up and down in these directions. Now, we talked about before how this cuts the axis in a kind of even way, like you can think of a pie being cut into thirds. So you'd expect if one is on the real axis, one slice, that is, one cut mark, then the other 2 should be kind of angled like that. Okay, it's not important to me for this sketch, for the practice, that you make those angles, but if you wanted to find them out, you could use the asymptote formula and the angle formulas. Okay, so let's apply now to find out where this actually breaks out. Let's apply the breakout formula. Okay, so we have our numerator and our denominator. So we write those out, n and d, and then we take the derivative of both. We plug in all of this information into the breakout formula, which I wrote right here. Once we solve for this, we get 2 solutions. It's a second order equation. That doesn't mean that all of the solutions are useful, but we need to evaluate which one makes sense. You'll notice right here that we only have 1 point where we're breaking out. We know that. If we're using the collision rule, we have 1 single point where we're breaking out. Now, it doesn't mean that we can't break back in, but does that make sense with our locus so far? We would have to have a real zero or a virtual zero and some kind of a gap in our migration path for that to happen. So really that shouldn't make sense. We know that we have a virtual zero up this way, one up this way, and then one out at -infinity. So it appears that that's happening. Everything is covered and happening as it should. So really, we just need to select if the -1 or the -3 makes sense. Now, unfortunately, it's not a quick toss out of which one is not in our migration path because they both are in our migration path. But the -1 makes more sense because you'll notice we were talking about them when we're colliding these 2 roots, these 2 poles. They're both moving. So at some point, the -3 point is being left behind. We're moving in this direction. So actually, the -1 makes more sense in this case. It is between 0 and -3. So if we're moving and we're colliding at some centralized point, that should be the -1 given the choice between the 2 of these. Okay? All right. We can finally answer the very last part of this question. Is it stable for any, or is it unstable for any k? And actually, no, we're completely, aside from the very first point when k equals 0, we're completely in the left-hand plane here. Now, if you completed, no, I'm looking at the practice kind of graph. If you completed this with the angle formula, of course, your movement will go out here into the right-hand plane at some point. Okay, and so I'm answering with respect to what I would assume that you had thought about and drawn. It'll be stable for all k greater than 0 in that case. Okay, now if you applied the angle formulas, there will be a case where it is unstable if you cross into the right-hand plane. Okay, but that concludes homework number 6, and that's all for problems here with our root locus and our GC design. Okay, see you next time.